All right. This is assignment 6D, and this is area under a curve. Okay, so here's in essence what we're going to be getting at eventually. Here's the grand picture and why we're doing what we're doing. So we learned antiderivatives, so for instance, if I gave you this x squared or something like that, a picture that ultimately looks like this, okay? That's what an x squared looks like. Now, what we've been doing is we've been creating these antiderivatives, okay? So we turn that into an x to the third and go 1/3, and then plus c. We're going to forget about the plus c here just for a second. What this, in essence, does is, if used properly, what it will do is it will find area underneath this curve to the x-axis. So say, for instance, I want to know what is the area from 1 to 3, okay? 1 to 3. So what is all of this area right here? All right, I want to know what is the area from 1 to 3. All right, ultimately what we're going to do is we are going to evaluate this using an integral, and that will tell us an area that we want. So we'll learn this in some upcoming lessons, and this will tell us what we want. Now, we're not quite to that point yet to do it the fancy method. Okay, to do it the fancy method. So what we're going to do, and what calculus people have done, and so it's a very tricky way of doing it. It's very clever and brilliant. But what they do is there's this guy by the name of Riemann, and he created these things called Riemann sums. Riemann sums. And so, in essence, what Riemann sums are is this. Say I do want to know that area from 1 to 3. Let's get rid of some of this unneeded area here. All right, I want to know what is the area from 1 to 3. Here we go. Third time's a charm. Here it is. All right. So what Riemann does is this. He takes this length from 1 to 3 and breaks it up into smaller increments, whatever they happen to be, smaller increments. And what he does is he usually makes rectangles out of them. So if I make rectangles out of these things, and if I just add the area of these rectangles, Riemann says that's close enough. That's close enough. So if I add up all the areas of these rectangles, that's good enough. Okay, and that's what a Riemann sum is. Now, some of you, like as you would be I, are saying, well, wait a minute. That area, the area of the green, is not the area of the red. Look at all this extra area that the green is getting. So that area is not exactly correct. And that's a true statement. That's why these are an approximation. So it's not going to be the actual true blue area, but it is a guess. It's an approximation. All right, now how the heck do I create these Riemann sums, and what are the different types of Riemann sums? All right, so let's take these rectangles, for instance. Okay, we have these different things. There's different types of Riemann sums. There is right hand or right side Riemann sums, and it'll be R, R-A-M. So R is for right. So what that means is this. If I have all of these rectangles right here, potential rectangles, what is going to be the height of the rectangle? Well, in a right Riemann sum, it would be, so I'll call this, searching for a different color. I'll call this rectangle A, B, C, and D, okay? If I am using a right-hand Riemann, what you're going to do is you're going to use the right-hand height of all of them. And then you're going to find the areas of those rectangles. Okay? There's a different type of Riemann called a left-hand or left side Riemann approximation. Okay? Right? So it's a left hand. And so the same idea is, however, the area of the height of these rectangles are determined by the left side of the rectangle. So in A, it would come from the left side of A. B, left side of B. And so you see in this situation, if I did this, the areas would be underneath the curve. So the area that I get from these rectangles is too small. So the right hand was too big, the left hand was too small in this particular case. All right, there is two more. The next one is a M-ram, and that is a midpoint, So what you do is you go, like for instance, in A, you go to the middle between where A begins, so you go to the middle and find the height where it hits the graph of the middle. All right, so be like in the middle, and then you create the rectangle in that regard. So you get a little extra, but you also cut out some. Like so, for instance, you get a little extra area, but then you're missing some area. And so that's an even closer approximation. Okay, the midpoint. And then last but not least is the trapezoidal approximation. Okay, it's the trapezoidal approximation. And this is what, if you recall what a trapezoid looks like, what one of these trapezoids are going to look like is you have a height and then it will look something like that. That's your trapezoid. Okay, that's what your trapezoids are going to look like. So, and that is going to be a trap. It's a trap. Admiral Akbar would be happy. All right, it's a trap. And so what you do is you take the height here and here and you create just these as straight lines. You create those as straight lines. And so to make that one work, you probably need to understand what the heck the area of a trapezoid is. And that's 1/2 the height, base 1 plus base 2. All right, so using my purple picture up here as an example, what we're going to consider, the parallel sides are the bases. And so what's going to happen is this is considered to be base 1 and base 2, or vice versa, and this is the height. All right, so like I always think of trapezoids as like being like, you know, something like that. So if you're anything like me and you need to think of it that way, think of this as kind of like as it's laying on its side. Have base 1 and base 2, and then your height. Okay, and so you find the trapezoids that way. Okay, let's go to our picture. Let's go to the actual assignment. They were nice enough to give us some values. So the interval in which we are taking all of these are from 1 to 5. All right, and we want 4 intervals. So using this first picture, here's 1, here's 5. And so if we're breaking that up into 4, it would be logical to go 1, 2, 3, 4. So there's 1, 2, 3, 4 intervals. All right, so in this one, so looking at my table, this has a height of 1, this has a height of 4, this has a height of 9, this has a height of 16, and a height of 25. Okay, from 1 to 5. So I don't really care what's going on over here or over here. It doesn't really matter. Okay, I'm only looking from 1 to 5. Again, here's 1, here's 5, broken up into 4 sub-intervals. All right. This one is going to be an L ram. So the left-hand side is determining the height. So of this first rectangle, the height is going to be 1. The second is going to be 4, 9, and 16. So the LRAM in this situation is going to be equal to base times height. So the first one has a base of 1 and a height of 1. The second one has a base of 1 and a height of 4. The third one has a base of 1 and a height of 9. And the fourth subinterval has a base of 1 and a height of 16. A way to simplify this math, if you have a consistent height or base, what you can do is you can take that base out. So I can, in essence, take this 1 outside. It has a consistent base of 1. And then what this, in essence, would be is 1 plus 4 plus 9 plus 16. It's, in essence, GCFing out a 1, or whatever the height is, the consistent height out every single time. Okay, so this is 2030. This has an approximated area of 30. Let me just get it all. Okay. So number 2 is the same type of question, but this is going to be an an RRAM. So let's again take a look at our various levels here. So again, we have heights of 1, 4, 9, 16, and 25. From 1 to 5. And the heights of these rectangles are going to be determined by the right-hand side. So of this first rectangle, the height is going to be 4, and then 9, and 16, and then 25. So the right-hand side of each specific rectangle is the height. So notice how, again, we have a consistent base. The base is consistently 1. If it's not consistent, you got to break it down similar to how I wrote down originally. But if they are consistent bases, you can learn these tricks. The base is 1, and then heights are 4, 9, 16, and 25. So this is what, 34 or something? I was right. Yeah. Okay. 54 is this approximation using the RRAM. So looking at these two things, the LRAM and RRAM, neither are the correct answer, but the correct answer would be in between the two things. One's an overestimate and one's an underestimate. Okay. All right, the MRAM. The MRAM. All right, so what the MRAM is consistent of is, so if the intervals are, for instance, right here, the midpoint would be in the middle. There, it'd be in the middle. Here, it's in the middle. Here, it's in the middle. This is determining the heights of the rectangles. And so if this is at 1 and this is at 2, the midpoint would occur when an x value has 1.5. The next one would be at 2.5, et cetera, et cetera. So if you look up to the table, I believe those values are given. So 1.5 has a height of 2.25. Uh, 2.5 has 6.25. 3.5, 12.25. 4.5, 20.25. And again, these are the heights of these various rectangles. And so this is our approximation in this case. But again, they're rectangles, so you can use the same tricks. So this has a base of 1 and heights of 2.25, 6.25, 12.25, and 20.25. Again, you can only do it this way when you have a consistent base, like this is 1, 1, 1, and 1. However, if the rectangles are, this one has a width of 1, and this one has a width of 2, and this one has a width of 1/2, something like that, you can't do it this way. You have to break it down, find the areas of each individual rectangle, kind of like the long way, kind of, again, how I kind of wrote down originally in number 1. Anywho, here we go. So this is 1 times all this stuff, so not a big deal. So this is 2.25, 6.25, 12.25, and 20.25. And these, the MRAM and the trap, are usually way closer of an approximation. All right, so this one's saying that the area is 41. Okay, so again, these are just approximations. These aren't the actual true blue areas, but we're approximating. Okay, and last one is the trapezoid. And so in the trapezoid, we have these various heights. So we have heights again of 1, 4, 9, 16, 25, because this is on x squared. All right, so we create these. And we have trapezoids. Okay, so we have to use the trapezoid formula. All right, so the very first trapezoid is going to be 1/2 its height. Again, the height is not up and down, but rather side to side. This has a height of 1, and base 1 plus base 2 would be 1 plus 4. Okay, that's the very first trapezoid. Plus. Okay, the second trapezoid, again, 1/2 its height, base 1 plus base 2, 4 plus 9, plus. The third trapezoid, 1/2 height, base 1 plus base 2. And the last, 1/2, 1, base 1, base 2. All right, now there's several different tricks that you can do when doing the trapezoid to make this process easier. Okay, like the rectangles, the height has to be consistent. If you do not have a consistent height, you cannot do this trick. Okay, if you do not have a consistent height, you cannot do this trick. And I advise you do it something like this, or there's one little thing. Okay, so say you did have different heights. Say you did have different heights. What I would still do is I would still GCF out a 1/2. So I'd say 1/2, and then I would say, 1 plus 4 plus 1, 4 plus 9 plus 1, 9 plus 16 plus 1, 16 plus 25. Again, that's assuming that these heights are different. Okay, here they're the same, but so GCF out the 1/2 if the heights are different, and then you can go to work out. Now, in this case, again, similar to the rectangles, the heights are consistent. So what I can do is I can GCF that out as well. So that would be 1/2, 1, and then I'm left with 1 plus 4 plus 4 plus 9 plus 9 plus 16, plus 16 plus 25. And it will always be like this. Notice what's happening. All of the, what I call inside numbers, are doubled, and there's just singulars on the edges. So back here, the numbers that are doubled are the inside numbers, and the edges are just singular. So there's a single 1, single 25, and these numbers are doubled. So the supreme, when you have a consistent height, is you take all that stuff out, and then you take a singular, and then you take, say, 2 times 4 plus 2 times 9 plus 2 times 16 plus a singular. So the edges stay single, and then you double everything in the middle. That's the quickest and easiest version of getting one of these answers. So here we did have a consistent. So this is going to be, I'll take care of the inside first, all the additions to this. 1 plus 2 times 4 plus 2 times 9 plus 2 times 16 plus 25. Okay, that's the inside. And then, in essence, 1/2 of that is 42. And so again, this is not exact. This is not exact. This is still an approximation. And our approximation is 42. Okay, last thing that I'm going to say before ending this video is this. The LRAM and the RRAM are similar to each other. One's going to be an underestimate, the other one is going to be an overestimate. Now, I'm not saying that the RRAM is always going to be an overestimate and the LRAM is always going to be an under. That's not true. All right? But what I'm saying is one's going to be over and one's going to be under. So these two kind of work with each other. These are the similar things, they work with each other. One's going to be an over and an under. Similar with the MRAM and the trap. Okay, one's an over and one's an under. So the actual area of this is somewhere between 41 and 42. These are usually the more exact approximations. These are usually more close than the rectangles, but these are usually more close. And again, one's going to be over and an under. How you determine that, I don't think they ask this very closely, is this. If a graph is increasing, say this was my F, and I notice that F is increasing. Okay, if I were to make a Riemann approximation, like what would I say if something is increasing and I take an LRAM? Well, the left-hand sides are determining the heights. So if something is increasing, this would be an underestimate. And an RRAM would be an overestimate. So again, take this and then take the right-hand sides. Okay, that's when something is increasing. Oops, I made a mistake on that one, sorry. Okay, so the RRAM would be an overestimate if it's increasing. If F is decreasing, okay, if F is decreasing, okay, an LRAM, let's check it out. What is an LRAM if it's decreasing? So left-hand sides are determining everything. If it's decreasing, this would be the overestimate. And the RRAM would be the under. Again, because take the heights from the right-hand sides. That's an underestimate. All right, so that is if the function is decreasing. All right, so that's the LRAM and the RRAM. So you'll notice on our actual graph here, you see that our function is increasing. So because it's increasing, I'll flash back to the picture, because the picture is increasing, notice how the LRAM was an under and the RRAM was an over. The LRAM was an under and the RRAM was an over. Makes sense. All right, the other two, the MRAM and the trapezoid, is determined by concavity. So let's take something that has a concave up, and I'll make a very blatant picture here. What's the area underneath this curve, you know, from here to here? What's the area underneath that curve? And so what you would do is, if it's concave up, let's take an MRAM. So the midpoint is determining it. And notice that the height of that rectangle would be missing a lot of area. Okay, the area of this rectangle is not the area under that curve. That would be an underestimate. And then if you take a trapezoid approximation, where you take the heights from the sides and you attach them, you see, oh, that area is too much. That's more than the area underneath that curve. So a trapezoid is an over. And again, this is when F is concave up. When something is concave down. Okay, what is the area between here and here? What is the area between there and there? Again, if you take an MRAM, okay, the height of the rectangle is going to be there, which is way more than the area underneath the curve. So again, the area underneath the curve is supposed to be just purely this. This is the area underneath the curve. And so I see that the MRAM is more than that. I see that the MRAM is more than that. So the MRAM is an overestimate. Again, this is when this is concave down. And the trapezoid approximation is we take the height on each of the sides and connect the two. And that's an underestimate. It's missing out on like all of this right here. So I see that the trapezoid is an underestimate. And I like drawing these pictures when I'm asked these questions too. So in our pictures over here, we see that our intervals, the intervals that we have are concave up. So when I have concave up, I know that the MRAM is an under and the track is an over. When it's concave up, I see that the MRAM is an under and the track is an over. Okay, that's it.